All right, so we're going to take a look at these examples. Now, all of these examples you can do. They're all chemicals that are on the sheet. Okay, I'm going to do the one example with you. Then you can try the next three on your own, but I will record them on this video. Okay, so the first one. We got sulfur dioxide plus oxygen gives us sulfur trioxide. They're gases. So what I do is I block off my reactants from my products. I don't do that first. The first thing I should do is simply balance my chemicals. SS, 4 O's, 3 O's. Uh-oh, 4 O's, 3 O's. Let's try two of these guys and two of these guys. Two S's, two S's. 4 O's plus 2 O's is 6 O's, 6 O's. There we go. 2, 1, 2. No problem. So what I do is I write on my reactant side. I deal with my SO2 first. I go to my chart and I look for my SO2. SO2 gas right there, negative 296.1. Hopefully you can see that in the bottom right-hand corner of the screen. So you find it on your chart, and it's negative 296.1 kilojoules per mole. Now, this is going to be positive. The chart says negative, but it's positive because we're breaking it up. It's on the reactant side, so it's positive. We times this guy by 2 because there's 2 moles to get a total of, see, 296.1 times 2 equals 592.2 kilojoules. So we did my SO2. Number from the chart times it by how many moles there are gives us how much energy that we're required to break, how much energy it takes to break it apart. Positives on the reactant side. O2. O2 is diatomic, so 0 kilojoules per mole. And we times that by 1 mole to get 0 kilojoules. So on this side, 592.2 kilojoules of energy is how much it took to break everything up. That's my reactants. This should remind you of figuring out molar mass, kind of. Now we've got SO3 on the other side, so we deal with the other side, SO3. So I go to my chart and I look for SO3. Down here, 395.2. This time it is negative because it's on the product side, negative 395.2 kilojoules per mole. Times it by 2 moles. To get 395.2 times it by 2 moles, 790.4. And that's going to be a negative because we're getting energy out when we form chemicals. So on this side, our products is negative 790.4 kilojoules. Now to figure out our total delta H for the whole reaction, delta H is equal to this plus this. So it's negative 790.4 plus 592.2. It's equal to negative 198.2 kilojoules. That's the delta H. This is an exothermic reaction. Right now, here's what I would like you to do is I'd like you to also sketch out a reaction pathway for this guy. So we start here with our reactants. And our reactants goes up this amount. So from there to there is 592.2 kilojoules to our activated complex where everything's broken apart. Then it's going to go down from here down to here. It's going to go down negative 790.4 kilojoules as our chemical bonds are formed. And lastly, our change in H, our delta H, is right here. Delta H, which equals negative 198.2 kilojoules. So that's the reaction pathway. We started off with these guys. We have to add in this much energy to break them apart. Radioactivated complex. New chemicals this guy's forming. And as that guy's forming, he's releasing a lot of energy. And more energy is released than is needed. So that's how you do this. Divide it down the line. Find your number from the chart for the chemical, times by how many moles there are to get the total amount of energy for that molecule. Then do the next one. Positives on the reactant side, negatives on the product side. I'll tell you what, there is a formula for this. I looked it up one time and it confused the crap out of me. And I was like, I'm just doing this the way I figured it out, because that way it makes good sense to me. All right, so pause the video here. And when you've done the first one, come back, unpause it, and check it out. Because I'm going to do the first one. H2 plus O2 gives me water. All right, so pause. All right, let's take a look at number 1. H2 plus O2 gives me water. So I build my chart here, my diagram there. Then I start with my H2. It's diatomic. Items that are diatomic have 0 kilojoules per mole. Oh, sorry, I forgot to balance this guy out. 2 H's, 2 H's, 2 O's, 1 O. We need 2 of these. We need 2 of these. We need 1 of those. No problem. Always balance chemical formulas first. 0 kilojoules times 2 gives me 0 kilojoules. That's pretty easy. Let's look at my O2. Also diatomic, 0 kilojoules times 2 gives us 0 kilojoules. Well, our product's reactant side is 0 kilojoules. Now, that's pretty easy. Our product side, H2O. Go to my chart. H2O. That one or that one? That one or that one? Well, here it says it's liquid, so it is this one, 285.8, negative. Negative 285.8 kilojoules per mole. We times it by 2 because there's 2 moles here. Then we get 285.8 times 2 equals 571.6 kilojoules of energy, and that's negative. Now, to figure out our delta H, we just add those two numbers together. Negative 571.6 kilojoules. That's it. It's an exothermic reaction. Hydrogen gas and oxygen combine together and release a lot of energy. And they just do this spontaneously. Well, do they? They actually don't. Hold that thought, though. So if I was going to draw a reaction pathway according to what we figured out here, we would start with our reactants. And then there is no kick up. And then we just go down 571. This is negative 571.6 kilojoules. And that is also our delta H because there was no activated complex. All right, so if you got number 1, good. Pause the video again and do number 2. All right, we're back with number 2 right here. We got KClO3, solid, leaves us with KCl and O2. So we build our chart. We look at our KClO3. We bring out this chart. Look at our KClO3. It's right here, negative 391.4. But because it is a reactant, this is going to be positive. Positive 391.4. Kilojoules per mole. And times it by how much? Oh, crap. I got to balance this. K is good, K is good, KCl, KCl, O3, O2. I need to get to 6 O's, so it's going to be 3, 2, 2, 2, 2, 3. So I got to times this guy by 2. 391.4 times 2 equals 782.2. That's plus. This is the only one on this side, so this side's going to be plus 782.8 kilojoules. Good. Now let's do our reactants. We've got our KCl. And we bring back this chart. KCl is right here. Oh, you can't see it. Negative 435.9. And this time it will be negative. Negative 435.9 kilojoules. Times it by 2 moles. This is kilojoules per mole. Times it by 2 moles to get 435.9 plus 2 is equal to negative 871.8 kilojoules. And let's do O2. Is 0 kilojoules per mole times 3 is equal to 0 kilojoules per mole, 0 kilojoules in total. And this side's negative 871.8 kilojoules. We can see that we're releasing more energy than we took in. That means this is exothermic. Add these two numbers together to get my delta H. So that's negative 871.8 plus 782.8 is equal to negative 89 kilojoules. That's our delta H for this reaction. Let's sketch out reaction pathway. All right, so we start with our reactants down here somewhere. No, maybe not quite down there. Down here. They go up to our activated complex. How much did they go up? They went up this amount. 782.8 kilojoules. That's how much energy was added to go from our reactants to our activated complex. Then we lost 871.8 kilojoules of energy to the environment. We went from our activated complex down to our products. Our delta H is this distance in here, between here and here, and that was negative 89 kilojoules. So we added in this much energy to break up these molecules. Then as these molecules were formed, we released this much energy. The overall change was that much energy. Huzzah. All right. Pause the video again. Try number 3. All right. And we're back with number 3. We've got the combustion of propane. C3H8O2 gives us CO2H2O. I'm going to remember to balance this time. C is 3, 1. Let's put a 3 in here. H is 8, 2. Let's put a 4 in here. O's 6 and 4 is 10, and we put a 5 in here. 1, 5, 3, 4. All right, so let's do up my dividing line. Let's deal with our reactants. We've got C3H8. Go to the chart, C3H8, right here, negative 103.8. But this is a reactant, so we do positive 103.8 kilojoules per mole, times it by 1. 103.8 kilojoules in total. That's plus. So we dealt with that chemical. Now we're dealing with our oxygen. Diatomic is 0 kilojoules per mole, times it by 5 to get 0 kilojoules. Add up this side. So plus 103.8 kilojoules. That's how much energy we added in to get these guys to break apart. All right, now let's do our reactant side, our product side, sorry. Start off with CO2. We go to our chart, CO2, negative 393.5. A lot of energy coming out when we build CO2. Negative 393.5 kilojoules per mole, times it by 3 moles to get a total of, let's see, 393.5 times 3 is equal to 1180.5 kilojoules in total. This is negative, right? Because we're releasing this energy into the environment. Now let's do H2O, and in this case our H2O is liquid. So we come on to here. We look at our H2O, we're getting a liquid, that's negative 285.8. This is a product, so it is negative 285.8 kilojoules per mole. Times that by 4 moles, because there's 4 moles there. And we get 285.8 times 4 is equal to negative 1143.2 kilojoules. Now we sum up this side. We get negative 2,323.7 kilojoules in total. Now to calculate our delta H, we take this number, add it to this number. So negative 2323.7 plus 103.8 equals negative 2219.9. That's a lot of energy being released. All right, now let's look at how this looks in our reaction pathway. Whoops. I guess I could have done that after. We start with our reactants somewhere up here. We add in 103.8 kilojoules of energy to get up to our activated complex. So we added in 103.8 kilojoules. Now after we added that in, then we lost, the chemicals themselves lost this much energy. It drops down, it tanks way down. If this was to scale, it would look even more dramatic, way more dramatic. So negative 23.7 kilojoules is gone out of the chemicals and into the environment. Because when the chemicals formed to make our products, energy was released. And our delta H, I've been doing that in purple. Our delta H is from here to here. And we get negative 2219.9 kilojoules. All right. I hope you were able to do these questions because there will be one on the quiz for sure. So I don't have a lot of other examples of this to practice on. So if you want to practice these again, try these exact same ones one more time. All right, I hope this was helpful. I hope you can do this on your own. And thank you for watching.